So this is where we left off in our last video. We tried to solve this equation and found that we ended up trying to find the square root of -1, right? So here, mathematicians in the past have done this and considered the result as something impossible to obtain, and they say that the square root of -1 doesn't exist. It's called imaginary. It's an imaginary number. So that's why we still call it imaginary number. But we're going to look at a few other equations that result in what you can refer to as complex numbers, complex roots. This is really a quadratic equation, and the answers to a quadratic equation, I call them roots, because the equation contains x squared and you end up saying x. So to get from x squared to x, you need to find the square root of x squared. So that's why they call them roots, and we say that they are complex roots. Alright, it can be a case where you have x squared plus 4 is equal to 0. What would be the answer here? If you subtract 4 from both sides, you have x squared minus 4, equals -4. And then x would be, so you find the square root of both sides. Square root of x squared is x. The square root of -4 is -4. Square root of -4. What did I say? The square root of -4, I rewrite it as the square root of -4. Now what you can do with this, you can consider it as the square root of -1 multiplied by 4. Remember, when you have more than one items multiplied under the square root sign, you can separate them, find the square root of each and multiply them. So it's the square root of -1 multiplied by the square root of 4. And this will give you, the square root of 4 is 2. We call this I2. But then, usually you put the letter after the number. So you could call this 2i and say that we have imaginary roots. Alright? Now, you could also have a case where you have, say, x squared plus 3x plus, let me see now, 4ac, 3 is 9, for, let's say, 15 equals 0. Alright? And you solve using whether the method of completing the square, or you solve using the quadratic graph, or not. Yeah, you're going to use the graph. Remember, you also, well, you wouldn't be able to use factorization here, but you could use the quadratic formula. So remember, the quadratic formula say x equal -b plus or minus the square root of b squared minus 4ac all over 2a. And here our a is 1, our b is 3, and our c is 15. Alright? So what we have is x equal -b, which is -3, plus or minus the square root of 3 squared minus 4 times 1 times 15 all over 2 times 1. See that? Which is -3 plus or minus the square root of 9 minus 15, 4 is what? 60. 9 minus 60 divided by 2. So x is -3 plus or minus the square root of 9 minus 60 is what? 51. So you have -51 over 2. So we have imaginary roots. They are -3 plus or minus the square root of 51 times -1 over 2. So what you would have here is x is equal to negative 3 plus or minus square root of 51i over 2. We could separate them, and one of 1 being plus, and the other x is negative 3 plus minus, we use plus already, minus the square root of 51i over 2, because we have imaginary roots here, right? Now, it would be interesting to see what the graph of these look like. You will remember that when you have a graph and you have your x-axis and your y-axis, and it's a graph of a quadratic function, you have a parabola. If you have it in the form ax squared plus bx plus c, it will be like this. And the roots occur at the points where the curve cuts the x-axis, where the curve intersects the x-axis. You also remember that if you have a negative ax squared plus bx plus c, the graph will turn up. It will have a maximum point. When a is positive, it has a minimum point. When a is negative, it has a maximum point. So again, you have the two values of x where the roots occur, right? Wherever the curve intersects the x-axis, you say x equal this number and x equal that other number. Both of them may be positive, both of them may be negative, all right? In some cases, the curve just touches the line, right? Now, what would the graph of these look like? Let's look at them using our graph plotter, GeoGebra. X squared plus 1 equals 0. All right, so we have x raised to the power of 2 plus 1 equals 0. X squared plus 1. What we would have is y equal x squared plus 1. Okay, x raised to the power of 2 plus 1. What does that look like? All right, so here, let me just fix this up, make it thicker so we can see it more clearly, right? So now, this is the graph of x squared plus 1. You see that there are no solutions. It doesn't intersect the x-axis. The x-axis is down here. The graph doesn't intersect it. Let us look at x squared plus 4 and see what that one looks like. Let's make an adjustment to this and turn it into x squared plus 4. Here, again, it doesn't intersect. In fact, it goes even further away from the x-axis. But what about this one, which we solved earlier? It is x squared plus 3x plus 15. So let's turn this into x squared plus 3x plus 15. My finger accidentally touched the slash. We take it off. So let's zoom out and see what is happening here. Oh, all the way up here. So it doesn't intersect the x-axis either. So these functions do not intersect the x-axis. So they have imaginary solutions. All right? So this is the simplest one, x squared plus 1. So looking back at x squared plus 1, that one is easy to remember. And you see it does not intersect the x-axis. All right? So you have no solutions there. So these are some examples of complex numbers. So we'll be looking more at this topic in our next video.